The following video will introduce you to sizing and topometry optimization in Genesis Structural Optimization for ANSYS Mechanical, or GSAM. GSAM is an extension that adds topology, topography, freeform, sizing, and topometry optimization to the ANSYS environment. The extension provides a reliable, robust, and easy to use interface which allows designer to set up structural optimization problems, post-processing them, and export the data within the ANSYS environment. I will solve a simple structural optimization problem, first with sizing optimization and then with topometry optimization. Finally, I will compare the results obtained from sizing and topometry optimization. Sizing optimization is a type of structural optimization used to design specific dimensions or sectional properties of structural members. In current implementation of GSAM, the sizing optimization is limited to thickness of shell properties. Topometry optimization is an advanced type of sizing optimization which is used to design structural dimensions or properties of an individual element. With topometry optimization, user can perform element by element sizing optimization. The user can get continuous variation of the dimensions of the elements in the design space. Topometry optimization can also be used as group by group sizing optimization capability. Let's start with an example. As you can see from the diagram, the pallet lifter arms are subjected to a pressure load. Here, objective is to reduce the mass of pallet lifter structure. It is subjected to constraints that the stresses should be less than 20,000 megapascals and the displacement at the tip of the arms should be less than 0.1 mm. Now let's open ANSYS Workbench. A static structural solution has already been set up in ANSYS Workbench. Now I will switch on the Genesis ACT extension in ANSYS. The Genesis icon will show up in ANSYS Workbench toolbox. Now open the ANSYS Mechanical to visualize the model by double-clicking on the model cell of static structural. As you can see, Genesis Structural Optimization toolbar is added in ANSYS Mechanical with GSAM extension. Now go back to Project Schematic window. I will bring the Genesis extension into our workbench simulation so that it shares the existing model information. Click and hold Genesis icon and drop it on model cell of the static structural. Now in ANSYS Mechanical, we can set up the optimization problem. Double-click on the setup cell of Genesis. First, I will set up the sizing optimization. Click on Analysis Settings under Genesis. Change the maximum optimization cycles to 20. If the maximum number of design cycles is reached, then design optimization process could be restarted using Genesis restart capability. Now from Genesis structural toolbar, add sizing or topometry node to project tree. Now we will define the designable region. Click on Sizing and Topometry. Now for geometry, select Complete Assembly except the fixation support and select Apply. Make sure that 14 bodies are selected. Next, in the design type, select Sizing as a type. For design variable creation, select Independent. This option will create one variable to design the thickness for each selected shell body. For design variable bounds, keep the default values. Now the next step is to define the objective. From Genesis structural toolbar, push the objective button. Now select the objective node from project tree. For response type, select mass. For goal, select minimization. Now we will define the constraints. From Genesis structural toolbar, add two constraint nodes. Select the first constraint node from project tree. For response type, select stress. For load case selection, click on load case selection and select yes for all static structural load cases. Select apply. For geometry, select complete assembly except fixation support. Enter the upper bound as 20,000. Now select the second constraint node from project tree. For response type, select displacement. Now click on load case selection and select yes for all static structural load cases. For geometry, select all four vertices of arms. Enter the upper bound as 0.1. Now right-click on solution and add element sizing plot to observe the thickness of each element. Add design history live plot to monitor the optimization process. Now right-click on Genesis in project tree and push solve. Check the optimization progress by clicking on Solution Information node. This does take some time, so I will skip the solve time. Now scroll down to check design cycle history. Here you can check objective function value and maximum constraint violation value for each design cycle. The total number of design cycles are 11. The final value for the mass is 1.54 into 10 raised to minus 5 kgs. Here we are getting hard conversions. That means objective value for two consecutive design cycles did not changes appreciably, satisfying all the constraints, but there could be some change in the design variable value. Now click on the element sizing plot. The blue color indicates thinner part and the red color indicates thicker part. The variation in the thickness can be seen in the color bar. Now click on Design History Live Plot. This allows the user to check best objective value and maximum constraint violation for each design cycle. The user gets a visual feedback how optimization proceeds. Now we will set up the topometry optimization. Go back to ANSYS Workbench. Drag the Genesis extension from Toolbox and drop it on the model cell of static structural. Now double-click on Setup cell of Genesis extension. This will open ANSYS Mechanical. Now you will be able to see another Genesis in project tree. Now click on Analysis setting under Genesis. Change the maximum optimization cycles to 25. Under Analysis Output Control, select Yes for element stress. This will print the element stress value for each element in post-processing file. Now, from Genesis Optimization toolbar, add Sizing or Topometry node. For geometry, select Complete Assembly except fixation support. Now in Design Type, select Topometry for type. For design variable creation, select Independent. Now I will add fabrication constraints so that optimization will not lead to non-symmetric part. For constraint 1, select mirror about YZ plane. This will maintain the symmetry of the structure about YZ plane. Next, for coarse method, select specified cell size. The coarse method is used to reduce the number of design variables and speed up the process. This option requires the user to specify dimensions for a box. This box will be used to divide whole space into uniform mesh of boxes. The elements whose centroids are within the same box are grouped together. A design variable is created for each group. Copy objective and constraints objects from first Genesis system and paste them to second Genesis system. Now add element sizing plot and design history live plot in solution. Now right click on solution and push solve. This does take some time, so I will skip the solve time. Now click on solution information. Now scroll down to check design cycle history. The total number of iterations are 12. The final value for the mass is 1.37 into 10 raised to minus 5 kgs. The table displays the mass of pallet lifter for each design cycle for sizing and topometry optimization. In sizing optimization, the mass is reduced by 28%, whereas in topometry, the mass is reduced by 39%. The figure shows that in case of sizing optimization, along the length of pallet arm, a uniform thickness is preserved. But with topometry optimization, you can get a variable thickness along the length of pallet arm, which results in more weight reduction. This completes the demo. I hope that it has helped you to get familiar with implementation of sizing and topometry optimization in GSAM. If you would like to learn more, I invite you to check other videos about GSAM. For additional information, please visit our website at www.vrand.com or email us at gsam.support@vrand.com. Thanks for watching.